After completing and discussing our lab to determine the volume of 1 mole of a gas, our class agreed as a class consensus that there are 22.4 liters in every 1 mole of gas at standard temperature and pressure. It's important to note, though, that this value of molar volume only works for standard temperature and pressure. This value is the same for every gas because the particles in a gas are so far apart that they don't really interact with one another. If you think back to last semester when we talked about Avogadro's hypothesis, it didn't matter what substance that it was. The pressure is based not on what type of particle, but how many collisions that there are. The volume is based not on what type of particle, but temperature and the pressure and the other variables. So it doesn't matter what type of particle, just how many particles there are and how they interact with their container. And as we already said, this value works for gases because they're so far apart. For solids and liquids, with the particles much closer together, interactions between particles make a difference. They stick together, they attract one another more. And so this value does not apply for solids and liquids. This molar volume can be used as a conversion factor in much the same way that the molar mass of a solid or liquid can be used as a conversion factor. So in this example, we know that we have 7.9 liters of oxygen gas, although it really doesn't make a difference what it is as long as it's a gas. And it says, there's another key thing here to note, it says that at STP. Again, this only applies for STP. We know there are 7.9 liters of gas, and our conversion factor says that for every 22.4 liters, there's 1 mole of gas. So we put the liter, in this case, in the bottom so that liters cancel out, and we're left with units of moles. So if you take 7.9 divided by 22.4, find that this is equal to 0.35. Again, I have to use two significant figures because that's how many sig figs are in 7.9. So 0.35 moles of oxygen gas. So this can be used much like the molar mass, only it works just for gases and only at standard temperature and pressure. So hopefully you can imagine that while the 22.4 liters in every 1 mole is wonderful if you're at standard temperature and pressure, it's not often that you're actually at standard temperature and pressure. So we're going to figure out a way to use this fact, but in a way that we can easily and quickly apply it at other conditions. So we're going to combine the three things that we know. We know that pressure is proportional to the number of particles. In other words, if we double the pressure, or if we double the number of particles, the pressure doubles. We know that pressure is proportional to the temperature. As the temperature gets bigger, doubles, the pressure doubles. We also know that pressure is proportional to 1 over the volume. That means if the volume doubles, the pressure is cut in half, or if the pressure doubles, the volume is cut in half. So I'm going to combine these three to make a little expression here. Pressure is proportional to N times temperature over volume. I just kind of combine those three into one. We want to get an equation out of this, so I'm going to rearrange it a little bit. Pressure times volume is proportional to number of particles times temperature. And this little symbol here that I've been using is called a proportionality symbol. What it's saying, it's the Greek letter alpha, and what it's saying is that we're missing some constant. If we take pressure times volume, it would be equal to some constant times number of particles and temperature. So we're going to try and figure out what that constant could be. So we're going to say P times V is equal to some constant. In gases, we call this constant R in T. We're going to figure out what that constant is by plugging in some pressures and volumes and number of particles and temperatures that we know. So pressure at standard temperature and pressure is 1 atmosphere. We just figured out that the volume at standard temperature and pressure is 22.4 liters. We're trying to figure out what this constant is. We'll call it R. The number of particles would be 1 mole. And the temperature for standard temperature and pressure would be 273 Kelvin. So if we rearrange and solve for this constant R, it would be 1 atmosphere times 22.4 liters divided by 1 mole and divided by 273 Kelvin. So we find that this value of R is 0.0821 liters times atmospheres all over moles times kelvins. This might seem like a pretty tedious process, but we're in luck. This letter R is known as the universal gas constant. And you can look this gas constant up for any combination of volume units, pressure units. So it's out there, it's known. I will provide you with several different units of R on the test. So at the end of the day, what this boils down to is we have this equation, PV equals nRT. This is called the ideal gas law. And the ideal gas law can be used if you know any 3 of the 4 variables, so pressure, volume, number of particles, and temperature. If you know 3 out of those 4, you can use this equation in combination with a known value of R to solve for the 4th variable. So say I know volume, number of particles, and temperature for something, I can solve for pressure. Say I know pressure, volume, and number of particles, I can solve for temperature. And R is a constant that you really just have to look up and match all of the units in the R value to. So we'll look at some examples of how to use this ideal gas law in the next video.